Welcome to an instructional lesson that is introducing the concept of nomenclature, that systematic way of naming compounds. And what we're doing in this first of a several series of lessons is introducing two types of compounds, ionic versus molecular. And this particular lesson is going to focus on ionic compounds. Ionic versus molecular, since we have two very different, of course I can't talk and spell, let me see, molecular, what we're looking at is two very distinct types of compounds, the way that they're built, what types of elements are involved in them, what types of bonds that they form with, and therefore two very different sets of rules for naming these compounds. Let's focus today on ions and ionic compounds, and in the next lesson we'll take a look at the molecular category. To understand ionic compounds, we're going to start with a very definition of an ion. I know that atoms are neutral. Ions are charged atoms. And let's just consider that with just an ordinary example from the periodic table. Let's take a look at, how about an atom of fluorine? If you look at the periodic table and find fluorine on your chart, you see that it has an atomic number of 9 and a mass number of 19. So just some information there from the periodic table about fluorine. And if I think about what that means is that there are 9 positive protons inside of a nucleus. 19 minus 9 gives us 10 neutral neutrons in the core, and it would arrange its electrons with 2 and then 7 in that second energy level. So just a basic Bohr model or solar system model of a fluorine atom. We understand that since the number of electrons are the exact same number as protons, that atoms are neutral. So electrons equal protons makes an atom neutral. So this actually is a very unstable electron arrangement. The reason is this energy level is not full. A second energy level would like to hold 8 electrons to achieve a noble gas configuration. Every atom on the periodic table would like to achieve the noble gas arrangement. Fluorine as an atom is an unstable arrangement. It would much rather take in an electron. Adding one more electron into that outermost energy level would give it the same number of positive protons, but now it would have 10 negative electrons and actually have a net charge of -1. And if we have a net charge of -1, it's no longer neutral, it's an ion carrying a charge. Atoms will either lose or gain electrons to become charged. If the atom has gained electrons, we know it to be a negative charge. We call it an anion. If atoms lose electrons, they become positively charged and we call them a cation. When I see the word cation, what helps me remember is that in the word itself is a little T for cat. Cation is the proper way to say that vocabulary word. And that T buried in this little word here reminds me of a positive sign. Cations are positively charged atoms. Anion is a negative ion. And what I can do there is use that AN as part of the beginning word and realize that that stands for a negative ion. Cation has a T buried in it. It's positive. A negative ion is an anion. So just some little helpful words there to help us remember those definitions. As we mentioned up here with an example from fluorine, let's take a small atom like lithium and denote what it might do in terms of forming an ion. On the periodic table, lithium has a mass number 7, atomic number 3, so it has two, that's a mistake. It has three positive protons. That's its atomic number. 7 minus 3 is 4 neutral neutrons. There's the nucleus structure of lithium. Its arrangement would have 2 electrons in the first and 1 more in the second energy level. That second energy level is not full. An atom of lithium is very unstable, simply because the outermost energy level is not full. It would like to have a noble gas configuration, and so if it's not full, it means that it would like to lose 1 electron. Outermost energy level is not stable because it's not full. If it were to lose 1 electron, this guy here, it would achieve a noble gas arrangement just like helium would. And helium, being a noble gas, is a much more stable arrangement. So if you lost 1 electron, I still have 3 positive protons, but now I only have 2 negative electrons. The resulting charge is a +1. When lithium forms an ion, it forms a cation by losing an electron. When fluorine forms an ion, it does so by gaining electrons, and when you gain electrons, you form an anion. Loss of electron positive, gain of electron is negative. So let's take a look at some simple models to help us drive this instance home. Take a look at the sodium atom to the sodium ion. With me on your periodic table, you can find sodium. He's number 23/11, atomic number 11. It helps you identify where sodium is on our periodic table. Atomic number is 11. So just to quickly bring up that periodic table, see sodium right here? It's in the first column, 3 rows down, just so we had a visual. That tells me in the nucleus of our sodium atom, we're going to place 11 positive protons. 23 minus 11 is 12 neutral neutrons. We understand that there's a total of 8 and then 1, giving us 11 electrons. So atoms are neutral. The positive electrons equal the negative electrons. Atoms are neutral. But this is a very unstable electron configuration. It's unstable because the outermost energy level is not full. It would like to achieve a noble gas arrangement, and it can do so by losing this electron in the third energy level. Losing an electron would still remain the same nucleus, 11 positive protons and 12 neutral neutrons, but now the configuration would go 2 and then 8 and stop. Therefore, over here we still have 11 positive protons, but they're now being balanced by 10 electrons, so the net charge now is a +1. There's a proton not being neutralized by an electron, giving us a net positive. The sodium ion is a cation. It formed a +1 charge. Well, where does that electron go? It's got to go somewhere. I bet out in nature there is an atom just dying to gain the electron. And that's exactly what chlorine would like to do. Let's model why. Remember where chlorine lives on the periodic table, way over here? It's in the group 7A, third period down. So knowing that its atomic number is 17, 17 positive protons, let's make that a little neater please. 17 positive protons, and 35 minus 17 is 18 neutral neutrons. 3 energy levels because it's in period 3. A total of 17 electrons to balance the 17 positive protons, giving us a net charge of 0. Atoms are neutral. But this is an unstable arrangement simply because atoms would prefer having their outer energy level the same as a noble gas, a full outer shell. Now, to achieve this, it's going to gain an electron. That energy level would like to gain. Sodium wanted to lose, chlorine wanted to gain. I see a beautiful relationship forming. This electron can be transferred from the metal to the nonmetal, forming what we call an ionic bond. When a metal loses and the nonmetal gains, we're forming a bond. So the result here is still 17 positives, 18 neutrals in that core called the nucleus, but now the configuration fills that outer shell with a 288 electron arrangement. 17 positive protons with a total now of 18 electrons gives us a net -1 charge. We call that anion, a negative ion. So here we see the basis of a beautiful relationship between a transfer that metals want to lose to achieve a noble gas, nonmetals want to gain to achieve a noble gas arrangement, and we have what is known as an ionic bond, a transfer of electrons from metals to nonmetals. I spelled that wrong, so I fixed it. Where metals like to lose, and remember, losing electrons makes it become positive, and they lose those electrons to the nonmetals, who are going to gain electrons and form anions. When we take into consideration a transfer of electrons where the metals lose and the nonmetals gain, we see this category of compounds known as ionic compounds, compounds built of ions. If magnesium, just to remind ourselves where magnesium lives, right here, it's atomic number 12, mass number 24, we'll just call it 24, rounding to the nearest whole number for that example. So 24 over 12, we'll say. Inside of the nucleus, we know there's 12 positive protons, 12 neutral neutrons, and the number of electrons must match the protons because atoms are neutral. 12 positive protons are electrically balancing the 12 negative electrons to make an atom neutral. However, the atoms are unstable in their electron configuration. They want to achieve the noble gas arrangement. So here we have 2 electrons in the outermost shell that need to be lost. It needs to lose 2 electrons to achieve the noble gas arrangement, the noble gas being neon with 10 electrons. When it does so, we'll see that as the ion and 2 8 electrons that are left, 12 positives and only 10 negatives leave me a balance of a +2 charge. When magnesium loses 2 electrons, it leaves itself with a +2 charge. Well, where do those electrons go? I mean, they got to go somewhere. If we revisit that element chlorine that we just looked at a moment ago, we remembered chlorine with its 17 positive protons. Its arrangement was 2, 8, and 7. Remember that chlorine would only have room to take in 1 electron. When it takes in 1 electron, its outer shell is full. So I can see if one of, let's say these are the 2 electrons here that need to be lost, I can see one of them going to this first chlorine, but I'm going to need to draw an entire new chlorine atom. So a second chlorine, 2, 8, and 7, to bring that second electron down here. What we're realizing is when magnesium needs to lose 2 electrons and chlorine, who only has room for 1, we're going to need 2 chlorines to neutralize the positive 2 charge from magnesium. The compound we formed is called magnesium chloride. And we'll talk a little bit more about how we name ions. We say the name of the positive, say the name of the negative, but end it in "ide." Excuse me. If magnesium loses 2 electrons, it's going to take 2 chlorines to neutralize it, to make room to take in 1 electron into the first and the second electron down here. The subscript, that's a vocabulary word, the subscript is telling us it takes 2 chlorines to balance the magnesium's charge. To name positive ions, we say the name of the element as it is. And then put the word ion after it. I wanted to name Al3+. I would call it aluminum ion. It lost 3 electrons. I want to name Ca2+. I'll call it the calcium ion. So I simply say the name of the element as it appears on the periodic table and add the word ion after it to let you know I'm not referring to a neutral atom. I'm referring to a positively charged ion. How do we name negative ions? Well, to name negative ions, we change the ending of the original element and remember, these will be nonmetals. Change the ending of the nonmetal name to an ending of IDE. Chlorine becomes chloride. Sulfur becomes sulfide. Fluorine becomes fluoride. Oxygen becomes oxide. Hear the negative ending with IDE. Some physical properties that ionic compounds share. When I think of ionic compounds, they're commonly referred to as salts. Ionic compounds are built of a basic building block known as a formula unit. For example, sodium chloride has a basic building block between ions of sodium and chloride in a repeating pattern over and over and over, making a crystalline solid. And I could keep drawing these where the crystal solid has a repeating pattern, and these are actually quite beautiful under the microscope. This crystalline structure is a repeating solid over and over. A formula unit is the lowest subscript ratio of that repeating pattern. For sodium chloride, they hooked in a 1:1 ratio. For magnesium chloride, they hooked in a 1:2 ratio. You would see 1 magnesium surrounded by 2 chlorines in our repeating structure over and over as it made its crystalline solid. And so here our formula unit, the lowest ratio possible, 1 magnesium to 2 chlorine. 1 magnesium to 2 chlorine. They're just a very large 3-dimensional crystal with this repeating pattern creating that formula unit, that repeating pattern. Ionic compounds are called formula units. The lowest subscript ratio in the ions is called that formula unit. So make sure that when we're writing formulas for ions, we write them with the lowest subscript ratio possible. They're commonly called salts. Ionic compounds are made of ions. We must have a positive ion hooking with a negative ion to create an electrically neutral compound. Our goal is to make sure the overall charge adds to 0 to make an electrically neutral compound. One positive charge electrically balances one negative charge to make it neutral. Ionic compounds, remember, are called crystals. They're always solids at room temperature and take an incredible large amount of energy to cause them to melt. Try melting table salt sometimes. It takes a huge amount of thermal energy. These are some common physical properties that ionic compounds share. Let's review. Let's give the name and the symbol of the ion formed when, for example, a sulfur atom gains 2 electrons. I'll go to the periodic table and I find sulfur and I see that its symbol is S. So I begin by writing the symbol S. Now if I just leave it like this, I would think it's an atom and it's neutral, but it gains 2 electrons. Gaining electrons forms an anion. Gaining 2 makes it a -2 charge, and we would name this as the sulfide ion. Hear that negative? IDE. Aluminum atom loses 3 electrons. The symbol for aluminum right here is Al. We begin by writing its symbol. If I leave it just as this, I would think it's a neutral atom. Loss of electrons makes a positive cation, and it lost 3. Aluminum ion is Al plus 3. A calcium atom loses 2 electrons. The symbol for calcium, Ca. The fact that it lost 2 electrons shows us that it's a +2, and we name this simply as the calcium ion. It is a cation, a positive ion. How many electrons were lost or gained in forming each ion? Well, Ba with a +2 charge, I should have grabbed that to make it superscripted. 2 positive or +2, doesn't matter which way you write it. We're simply going to name the element. The name of Ba is called barium. If you're still working on that periodic table skill, remember you just are going to slide down. Right here is where we'll find barium. Ba is barium. And I just say the name followed by the ion, barium ion. As, 3 negative. As is right here. Can you see its name? Arsenic, arsenic. But when it's negative, we name it with an IDE. This becomes arsenide ion. The arsenic changes the ending to arsenide ion, a negative ion. Cu stands for copper. Find it right here. See the name for that is copper ion. I have to tell you there's going to be a Roman numeral in that name telling us that it's a +2 charge. More on this coming. Transitional metals are ones that we don't know the charge by where we look. And so therefore, well, I'll tell you the charge with the Roman numeral, but there's a lesson related to that. And S, this is the element sulfur. Sulfur gets changed to ide when I write out its formula, sulfide. Perhaps you've noticed there is a very specific pattern in predicting how many electrons are lost or gained for the representative elements. I'd like you to take your periodic table out. Maybe you have it out already, but we're going to write on it. What we're going to do is to create a, your test-taking tool periodic table. Every time I add additional notes, I'd like you to do that. We understand that there's a pattern in predicting, and I remember mentioning to you that one of the things we did was to separate out the metals from the non-metals. And you put this on your periodic table, printed from Blackboard. I know that over here are the metals, and I know that metals are positive. And on this side of the border, we have nonmetals, and nonmetals are negative. So I just wanted to remember that that border separates metals from nonmetals. First of all of these elements in the first column, group 1A, what they have in common is that they have one electron in their outermost energy level. And when they lose one electron, they will always form a +1 charge. On your periodic table, on top of hydrogen's group number 1A, please place above it +1. That way you'll remember, just as a visual, that all of these Li+1, Na+1, K+1, Rb+1, and so forth, they're all positive ones. Let's make the same note on top of beryllium's family. Beryllium will always be a +2 when it loses its 2 electrons in the outermost energy level. +2 for beryllium, Mg is a +2, calcium is a +2, strontium +2, barium +2, and so forth. These metals in group 2A have a periodic trend of all being a +2. Excuse me. Next, find the box of aluminum. Not on top of the column, but in the box of aluminum, I want you to write a +3. Aluminum is a metal through and through. It is a +3 charge when it loses its 3 valence electrons. I cannot know boron or anything underneath it because of the transitional metals that we'll need to go through before we get to the other one. So only in the box of aluminum. Let's find helium's family, the noble gases, and remind ourselves that group 0, sometimes called group 8A, it's called group 0 because these noble gases, they're the envy of everybody up there. They will never lose or gain electrons and become an ion. Helium will always be a neutral atom. Neon is always a neutral atom. By putting a 0 there, I'll remember that they're never charged. Fluorine, chlorine, bromine, and iodine are all in group 7A. When they gain an electron, they'll be a -1 charge. Fluoride, F-1. Chloride, Cl-1. Bromide, Br-1. That same periodic trend for oxygen's family. Oxide, O-2. Sulfide, S-2. Selenium becomes selenide, Se-2. Nitride and phosphide would always be -3s. If they have 5, they need to gain 3 to get over to neon. Carbide, silicide, -4, and in the box of boride is a -5. I'm also going to add in some notes just for these 3 elements here. In the box of zinc, I want you to tell yourself that it's a +2. Write that in the box of zinc that it's a +2. It does not have a variable charge. Do the same for cadmium, and in the box of silver, put a +1. Silver, Ag+1, cadmium and zinc are always +2. Aluminum is a +3. The other ones I know for positives are hydrogen's column, always +1, and beryllium's column, always +2. All other metals, and there's a lot of them, require a Roman numeral in the name. And again, this is a lesson coming. I'm just seeding it because I cannot look and know what their charge is when I'm naming it. I meant to write in their name. Alrighty. So here we have all other metals. Hydrogen's family I know is +1. Beryllium's family I know is +2. Aluminum +3, zinc, cadmium +2, silver +1, and that's it for the metals. Remember the metals, these guys to the left of this border? Those are the only ones I know with certainty what their charge is based on where they live. Otherwise, you will be told their charge using a Roman numeral, and the reason is it has these choices. In nature, iron can be a +3 or it can be a +2. I would not know based on where it lives. And to develop a further understanding of that requires additional knowledge that's coming. Just be patient and trust me that it's coming. So to name this ion, I'd have to call it iron Roman numeral 3, or this ion is iron Roman numeral 2, and now you know what charge to use when creating an ionic compound. For now, the takeaway is for these tall columns, the representative elements, those group A's, we've given ourselves a tool page for predicting their charge as they go from neutral atoms to ions. In the next lesson, we'll pick up talking about molecular compounds and the covalent bond. You may begin that lesson when ready.